Today we'll be talking about green chemistry and its applications. So what is the issue at hand, first of all? Today one of the most important global issues is climate change, and the biggest challenge it poses is how to prevent it using sustainable energy and renewable resources. And this is where green chemistry steps in.
Green chemistry is an area of chemistry and chemical engineering in which the purpose is to find alternative chemical methods and processes to the ones currently used to avoid the production of harmful substances.
Now let's talk about some applications of green chemistry, some real-life examples of green chemistry being used today. The first of these is carbon dioxide capturing. So what is carbon dioxide capturing? Well, CO2 capturing is basically the process of capturing waste carbon dioxide from large producers of carbon dioxide. Some of these include fossil fuel energy facilities, natural gas processing plants, amongst a few others. And the purpose is basically to store the carbon dioxide away, typically in an underground facility, so it does not enter the atmosphere again. Now, the current carbon dioxide capturing method is called carbon scrubbing. And basically, if you look at this diagram, flue gas, which is gas filled with contaminants, passes through this vent or chimney. And before it enters the atmosphere, it must pass through the absorption column. What happens in the absorption column is it's filled with liquefied solvents, which are amines. And basically what these amines do is they help trap the carbon dioxide. A typical amine that is used is monoethyl amine. And if you look at this reaction, the carbon dioxide basically gets trapped or captured by the amine. Now, the only issue with this method currently is that, first of all, the amine solvents must be kept at quite low temperatures to keep them in liquid form, which first of all takes energy. And also the amines have the possibility of degrading, which leads to inefficient carbon dioxide capture. So this is where the green alternative steps in. The green alternative is known as the membrane process. And again, if you look at this diagram, the flue gas passes through the vent or chimney and tries to get into this atmosphere. But before it does so, it must pass through this membrane. And this membrane basically filters out the carbon dioxide. But it must have very specific properties, including high carbon dioxide selectivity, thermal and chemical stability, and must be resistant to plasticization and aging. The largest obstacle with this method right now is that the more permeable this membrane is to other substances, the less selective it becomes to carbon dioxide, which is the exact opposite effect of what we want.
So the second alternative method is polymers that are made from carbon dioxide. So what are polymers from carbon dioxide? Reducing the anthropogenic carbon dioxide emission in the atmosphere has become an urgent environmental and climate issue for today's world. Because carbon dioxide is naturally occurring, abundant, inexpensive, non-flammable, and renewable chemical compound, it is a very promising feedstock for the chemical industry. A number of processes have been studied for carbon dioxide recovery, but as the name suggests, polymers from carbon dioxide are cyclic carbonates synthesized by carbon dioxide. So what is the method? Carbon dioxide is reacted with energy-rich rings such as oxidants to produce cyclic carbonates. Cyclic carbonates are particularly important as they are non-toxic and biodegradable with high boiling points and flash points that are easily produced from oxidants such as ethylene oxide and propylene oxide in the presence of tetrabutyl ammonium bromide. So the applications of polymers from carbon dioxide. Green polyurethane was the first modified hybrid polyurethane synthesized without the use of any hazardous isocyanates during the entire production process. What isocyanates is the functional group with the formula R bonded with nitrogen double bonded to carbon, which is double bonded to oxygen. And green polyurethane formulation combines the mechanical properties of polyurethane and chemical resistant properties of epoxy binders. Some applications of polymers synthesized from carbon dioxide can include their use as green solvents for degreasing oily steel, paint stripping, packaging, coating electronics, enhanced oil recovery, and barrier layers.
Okay, now let's talk about some of our own ideas that we came up with, some really basic ideas that we think might go forward to becoming greener methods. The first of these is a water-based lithium battery. So this theoretical battery that we thought of was using lithium and water. Lithium is a very strong reducing agent, and water exposed to oxygen can be a fairly good oxidizing agent as well. So according to this theory, the following half reactions can occur. And if you look at this diagram, using two very abundant and renewable resources, water and oxygen, along with lithium metal, a fairly large amount of voltage can be produced. Commercializing a battery based on this simple reaction could revolutionize batteries altogether. The second idea was extracting heat from thermogenic plants. First of all, thermogenic plants are plants that give off a large amount of heat from their bodies. Such plants are known to keep their surrounding air temperature as much as 30 degrees higher than normal atmospheric temperature. These are particularly useful because their highly exothermic property can be used as a heat source to generate energy for a further purpose. For example, if such plants are grown in a greenhouse that is able to extract the heat generated by all thermogenic plants, the heat can be used to power an output load depending on how much heat is extracted.
Another method is smart fluids and structures. One of the largest challenges of the architectural industry is finding environmentally friendly resources to build and rebuild large structures. Another one of their challenges is to be able to reuse as much of the original material in a building as possible when demolishing it for a new one. Concrete, stone, and plaster are just some of the many common materials used in modern buildings. A new material that can possibly be used is smart fluids. Smart fluids are able to change their state of matter from nearly liquid to almost completely solid when an external electrical or magnetic field is applied. Its structure can change in the following way under such circumstances. As you can see in this picture, when the magnetic field is off, the magnetic particles flow randomly like they would in liquid form. However, when the magnetic field is on, the applied field creates a structure that increases viscosity. Thus, the smart fluid actually acts like a solid. Using this property of smart fluids, such materials can be used as dynamic reinforcements in bases of large buildings. They can even be easily reused as they change structures from solid to liquid very easily.
Finally, we're going to talk about two areas where alternatives must still be found. First of them being fireworks. Now, despite fireworks being a spectacular phenomenon to watch, their environmental impact every year worsens the atmosphere more and more. Fireworks work based on the release of various metals. Some of these provide color, others which are just there for the necessary chemical reactions. And as you can see from this diagram, fireworks release what are called heavy metals, being lead, chromium, and antimony. Now, these heavy metals lingering in the atmosphere not only increase health risks for humans, they thicken the atmosphere and trap greenhouse gases, which we know is bad. The US alone uses about 2.5 million pounds of fireworks every year, and even India uses the most amount of fireworks during its Diwali festival, and all of these numbers spike during the New Year's Eve. And unfortunately, no alternative to fireworks has been found yet.
Another one of these processes that is very harmful to our environment is mining. Unregulated mining has the potential to release harmful substances into the soil, air, and water. Today, many governments enforce regulations on companies to ensure minimal harmful effects on the environment. As more mines open in countries with varying levels of environmental protection, it is essential to enforce safe mining practices. Mining depends on fossil fuels, which provides the energy needed to operate a mine. Many countries have no regulations on the use of fossil fuels for mining, resulting in very high pollution emissions. Thus, environmental standards are required for larger countries like China and Russia and other developing countries that mine in large volumes. Furthermore, mining is a process that greatly impacts the biodiversity and the landscapes of the land located both in and outside of the mining site. The effects of this damage are continued way after the mine has shut down, including the addition of greenhouse gases to the environment, the death of the flora and the fauna, and the erosion of the land and habitat. Current mining techniques require high amounts of water for the extraction, processing, and waste disposal. Water waste from these practices pollute the water sources and deprive water supplies from the surrounding regions. Although there are rules and regulations in place to minimize the effect of mining, there are currently very few alternative methods to mining that does not result in a harmful environmental impact.
Okay, so in conclusion, green chemistry can help the world move towards safer industrial processes that will ultimately impact each of our daily lives. So don't just brush this off as another boring presentation, because caring about green chemistry ultimately means caring about our future.